Today we'll continue exploring the application of single, double, and triple integrals in solving real-world problems. In this second part of our video series, we'll further develop the water discharge formula for a triangular weir, but this time we'll derive it using a double integral. So let's get started. So here we have the triangular weir from part 1, which we discussed in the previous video. Now we'll plot this triangular region in 3-dimensional coordinates, and to simplify, we will focus on just half of the triangular weir. Since the two halves are symmetrical, we can derive the discharge formula for half and then multiply by 2 to get the final discharge formula. Let's set up our 3D coordinate system and plot the half triangular region. This point is at the origin. This is the y-axis, so the value of y at this point is h, based on the original sketch, and this is the x-axis, so the value of x at this point is w over 2. This region represents the cross-sectional area of the weir, which can also be described as a velocity field, where its point has a corresponding velocity. If we imagine its velocity at every point in this area as a height extending vertically, it forms a 3D object like this. Since fluid discharge is defined as the product of area and velocity, the volume of this 3D object directly corresponds to the discharge. This is because calculating the volume of the 3D shape involves multiplying the area by the height, which in this case represents the velocity at its point. Now, by visualizing its point's velocity as a height in a 3D object, we are effectively creating a solid whose volume represents the fluid discharge. This idea uses the direct relationship between area and velocity to conceptualize a discharge in 3 dimensions, making it easy to understand why discharge can be thought of as a volume in this representation. The approach is also effective in helping visualize the link between the 2D cross-sectional area and the resulting flow rate by mapping it into a 3D space, which is a useful way to grasp the discharge concept intuitively. Now let's view this 3D graph clearly using Mathematica. In this representation, we assume that W is 10 and H is 15. So this surface is the velocity function v of xy equals the square root of 2gy, and below it is the xy plane. Now we are only interested in finding the volume above the triangular region and below this surface. So the volume that we are interested in is only this one. Now before we can calculate the volume, we must first establish our region on the xy plane by determining the equation of this line. Let the coordinates of this point be x1 equals w over 2 and y1 equals 0, and let this point be x sub 2 equals 0 and y2 equals h. Consequently, we can state that the slope of this line m is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1, which simplifies to m equals h minus 0 over w minus w over 2. Thus, we have m equals negative 2h over w. The equation of a line is y equals mx plus b, where b, the y-intercept, is h. Substituting these values, we find y equals negative 2h over w x plus h. Rearranging, we obtain y equals h minus 2hx over w. We can denote this region on the xy plane as r, while this surface is simply defined by the velocity function v of xy equals the square root of 2gy. Okay, the volume of this figure is given by the double integral of the square root of 2gy over the region R with respect to the A. Now, we have to remember that this function does not define the region. This one is the surface. Now, our region is the following based on this graph. Okay, now since we have already defined our region, we can now plug in the limits of integration for this double integral. Okay, let me copy this equation first. Okay, so now the volume is equal to the double integral the square root of 2gy. Let's integrate with respect to y first. Later, we will also calculate the volume by integrating with respect to x first. Okay, so the limit of integration y equals 0 from y equals 0 to y equals h minus 2h over wx, and then from x equals 0 to x equals w over 2. Now we can break this expression. We can break down this expression, and we are going to write the square root of 2g at the front because this is just a constant term. So x equals 0, x equals w over 2, and then y equals 0, y equals h minus 2h over w x, and the square root of y can be written as y to the power 1/2, and then dy dx. So volume equals the square root of 2gy, 0 w over 2. Now the integral of y to the 1/2 is y to the 3/2, and then we have to reciprocate this exponent, and then multiply this to y to the 3/2, 2/3 to the times y to the 3/2. This is the integral of y to the 1/2, and then the limits of integration is y equals 0 to y equals from y equals 0 to y equals h minus 2h over wx, and then dx. Now plugging in the limits of integration, 0 w over 2, 2/3, and then let's plug in the upper limit, so h minus 2h over wx to the power 3/2, and then now let's plug in the lower limit, y equals 0, so 0 to the power 3/2. Okay, so this is just 0, and then dx. Now v equals the square root of 2g, 0 w over 2. Let's put 2/3 outside, and then and then h minus 2h over wx to the power 3/2 dx. So volume equals 2/3 square root of 2g. Now to integrate this expression, first we need to find the derivatives of the inside expression. The derivatives is 2h over w. Then we have to reciprocate it, w over 2h, and then the inside function, x, and then increase the exponent by 1, so 3/2 plus 1 is 5/2, and then multiply by the reciprocal of this exponent, so tophet, and then we have to evaluate this from x equals 0 to x equals w over 2. So volume, so 2 times 2 is 4, 3 times 5 is 15, and then square root of 2g, w over 2h, h minus 2h over w, plug in w over 2 for x, so w over 2, and then raised to 5/2, and then let's plug in the lower limit, h minus 2h over w, the lower limit is 0 to the power 5/2, close. Okay, so v equals 4 over 15 square root of 2g w over 2h, and then let's simplify this expression. W cancel, 2 and 2 cancel, h minus h is 0, so this is essentially 0, and we are left with this expression, so 2h over w times 0 is 0, so we are left with h, so negative h to the power 5/2. Then okay, so we forgot to put the negative sign here because the derivative of this of the inside function is negative 2h over w, reciprocate the negative. So that is negative. Here is negative, and here is negative. So negative times negative, this will become positive. So in other words, volume equals 4 over 15 square root of 2g w over 2h h to the power 5 halves. Now let's revisit our figure here, our sketch. Tangent theta over 2 is equal to opposite over adjacent. So this is w over 2 over h. In other words, our w is equal to 2h tangent theta over 2, which we can substitute it to here. So the v equals to 4 over 15 square root of 2g. Our w is 2h tangent theta over 2 over 2h h to the 5 halves. So volume, so we can cancel this 2h. So volume equals 4 over 15 square root of 2g tangent theta over 2 h to the 5 halves. And this is the discharge for the half of the weir. So this is q over 2. So to find the final discharge, we need to multiply this expression by 2. So 2 times 4 over 15 square root of 2g tangent theta over 2 h to the 5 halves. So our final discharge is 8 over 15 square root of 2g tangent theta over 2 h to the power 5 halves. So this is the total discharge. Okay, now let's calculate the volume by integrating the double integral with respect to x first. And we must expect that we will get the same answer. Okay, so let me copy this equation first. Okay, so before we integrate the this double integral with respect to y first, as follows. Now we are going to evaluate the double integral by integrating with respect to x first. So okay, so the square root of 2gy dx dy. Now let's draw our graph, graph in the xy plane first. So this is our x, this is y, and this is h, and this is w over 2. The equation of this line is y equals h minus 2h over wx. Now in terms of x, now we need to solve for x, no, in this equation. So 2h over wx equals h minus y. Therefore x equals w over 2h h minus y. So the equation of this line with respect to x is this one. So if we integrate first with respect to x, like this, so from x equals 0 to x equals w over 2h h minus y, and then with respect to y, from 0 to h, so y equals 0, y equals h. So this is the limits of integration if we differentiate, if we integrate rather, if we integrate the double integral with respect to dx first, with respect to x first. Okay, so let's evaluate this integral. Again, we need to break down this expression and put the square root of 2g at the front. Y equals 0, y equals h, and then the square root of y can be written as y to the 1/2. And now we have to write the integral first. So x equals 0, x equals w over 2h h minus y, and then y to the 1/2 dx dy. Now so the volume is the square root of 2g, y equals 0, y equals h. Now y is a constant with respect to x, so the integral of y to the 1/2 with respect to x is just x y to the 1/2, and then the limits of integration is from x equals 0 to x equals w over 2h h minus y, then dy. Okay, so volume equals the square root of 2g, integral y equals 0, y equals h, and then plugging in the upper limit. So we have w over 2h h minus y times y to the 1/2, okay, and then minus if x equals 0, then this is 0, and then dy. Now simplifying, y equals 0, y equals h, so this is equal to w over 2h y to the 1/2 times h. minus, okay, I will not proceed like this. Okay, so we can distribute y to the power 1/2 to the expression inside the parentheses. So we will just consider this as constant. So w over 2h times h to the power h y 1/2 minus y to the power 3/2. Okay, and then dy. Now, since this is a constant term, we can just write it at the front. So v equals w over 2h square root of 2g, y equals 0, y equals h, then it's y to the 1/2 minus y to the 3/2 dy. So volume equals w over 2h square root of 2g, and then the integral of this expression is h y to the 3/2 2/3 minus y to the 5/2 2/5, and then our limits of integration is from y equals 0 to y equals h. So volume equals w over 2h square root of 2g, and then 2/3 h, plug in the upper limit, h to the 3/2 minus 2/5 h to the 5/2, and then when y equals 0, then this term is 0, this term is 0, so all of those is 0. And then simplifying, w over 2h square root of 2g, then 2/3 h times h to the 3/2 is h to the 5/2 minus 2/5 h to the 5/2. So volume equals w over 2h square root of 2g, and then 10h to the 5/2 minus 6h to the 5/2 over 15. So v equals w over 2h square root of 2g 4 over 15 h to the 5/2. Now we have already shown before that w is equal to 2h tangent theta over 2. So let's substitute this expression into this equation. So we have 2h tangent theta over 2 over 2h square root of 2g 4 over 15 h to the 5/2. So we can cancel 2h and 2h, and then let's put this numerical coefficient at the front, 4 over 15 square root of 2g tangent theta over 2 h to the 5/2, and this is equal to half of the discharge. So to find the total discharge, we need to multiply the volume by 2. So the total discharge is equal to 8 over 15 square root of 2g tangent theta over 2 h to the 5 halves, which is the same as the previous result. Okay, in the next video, which is the last part, we are going to deal with this problem using the triple integral. Thank you.